We're now going to look at section 8.4, Introduction to Parametric Equations. A parametric equation is where we take the normal variables x and y and define them both in terms of a third variable. So both x and y become dependent on this third variable called a parameter. The typical letters we'll see used for the parameter are t and theta, although other letters could be used. Those are the most frequently used ones. Theta when it's trigonometric functions that are involved, and t otherwise. And what we get when we define x as a function of t and y as a function of t is a set of parametric equations. That's supposed to be a y. Sorry, let me back up and fix that. Doesn't quite look like a y to me. There we go. So that would be a set of parametric equations, and if f and g are both continuous on an interval I, no breaks, no skips, just a nice, no asymptote, vertical asymptotes. If you have continuity on an interval, it creates what's called a plane curve. And that's going to be a curve that exists in the xy plane. Okay. So, and again, the letter t here, or theta in other problems, represents that is called the parametric, or it's called a parameter. Okay, so here's an example. If we had, for example, x equals t squared and y equals 2t plus 3, and we're asked to graph this plane curve on the interval from -3 to 3, then as we would do with a lot of the first brushes up against new graphs, we're going to make a table of values. And later we'll find if maybe there's a shortcut or a faster way to do this. But for right now, let's just make up a bunch of values for t on our interval. I like integers because they're easy to calculate. Of course, you could use other numbers in that interval, like square root of 2 or something, but why would you? It makes for a harder problem if you do that. All right, so I'm going to figure out what x is. Remember, it's just the square of t each time, so just square the t value and get the corresponding x values. And then for y, we're going to substitute into 2t plus 3, so 2 times -3, -6 plus 3 is -3. Substituting in for -2, you get -1. Substituting in -1, you get 1, and 3, and 5, and 7, and 9. So, let's set up our axes. Notice that the x values that we're going to be graphing have a low value of 0 and a high value of 9. So I'm intentionally giving myself lots of room in the positive x direction. Notice that the y's have a low value of -3 and a high of 9. So I'm going to have to sort of squeeze things in here. And -3. Okay, and the x's go from 0 to 9, so 5, 6, 7, 8, 9. All right, so let's see if we can plot those points. 9, -3 is my first point, and I'm going to plot that. And the other thing that's sometimes done to track where the thing is that this is tracing when it was, because the parameter t a lot of times stands for time. And you might be thinking, well, how can you have negative time? Well, that's not impossible. Time is just a relative thing. So if I snapped my fingers and said, okay, that when I snapped my fingers, that was time 0. Obviously, there was time before I snapped my fingers, and that's what we would call negative time. So time -3 is, say, 3 seconds before I snap my fingers. That's where the particle was, if this is a particle in motion. All right, so anyway, so a lot of times you'll want to label the point with the time it's there, because otherwise the t won't show up in the graph, because we're just graphing the x's and y's in the plane. All right, so the next point is at 4, -1, and it gets there at t equals -2. The next point is at 1, 1, and it gets there at t equals -1. Excuse me. The next point is at 0, 3. It gets there at time 0. Notice I keep saying time. Usually that's what t stands for, so I may default just say time instead of t. Please excuse me if that isn't actually what t is measuring in some particular case. Anyway, at time 1 we're at 1, 5. At time 2 we're at 4, 7. It's about right there. And at time 3 we're at 9, 9. Now, if this had asked us to graph from -infinity to positive infinity for t values, we would want to extend this graph forever. But in this case, we're only graphing that part of it. So we're starting here at t equals -3. And to me, it appears that we have a parabolic shape. That's why you graph a lot of points, is to sort of figure out what the shape is. And I think you'll maybe agree that this is a parabola. And so this is the path that the particle takes. Now, one thing that we can do with parametric equations is have a direction of movement. This is actually moving from -3 as a t value until you get to +3. So putting a few arrowheads along the curve tells you the direction of movement. Okay. So we'll want to do that each time that we graph a parametric equation. Is we're going to always want to indicate the direction the curve takes as t increases. Now, another thing that's done with parametric equations is to say, okay, well, if that is a parabola, isn't there an equation that would give me the parabola that this travels along? And the answer is yes. So what we're going to do to find that equation is do something called eliminate the parameter. So let me write the equations over here again. To eliminate the parameter means to get rid of t. And what you want to do in a case like this one is, this is a case where there are no trig functions. When there are trig functions involved, we're going to change our approach slightly. So since this doesn't have a trig function in it, pick one of the two equations and solve it for t. So the y equation to me seems like the one that would be easier to solve for t, because otherwise I'd have to end up having a plus or minus radical involved, and I don't really want to do that if I don't have to. So I subtracted 3 from both sides, and then I divide by 2. And then take that expression for t and substitute it into the other equation. So this would be x equals y minus 3, over 2, that's a minus sign right there, squared. And since it's a parabola, we should write this in standard form. So I'll want to distribute the exponent to the numerator and denominator. Of course, 2 squared is 4. And then multiply both sides by 4. And it's now in the standard form for the equation of a parabola. And we can look at this equation and see that the vertex would be at 0, 3. And if you look at the graph, that's exactly where it is. And we could set 4c equal to 4 and c equals 1, which means it will either open up or to the right. And then because it's y squared, we know that it either opens left or right because it's not a function when y is squared. And so this seems appropriate because with y squared, we're opening left or right. Positive c means we're opening to the right for sure, and that's where ours is. Now, this equation is accurate, but it actually gives us the whole parabola, and we want to only graph this part of it. So if we were to say, well, x has to be between 0 and 9, that's not a false statement, but what would make sure we get all of those points is if we were to say that we're going to let y be something that varies from -3 to 9, and that would capture all of these points. And so with that addition to the equation of that parabola, that tells us what points we're graphing on that parabola. Now, to get the direction of movement, you will have to go and figure out, like we did with the table earlier, as t increases, what direction are we moving? So just pick a couple of t values on that parabola, plot them, and realize that that's the order you're going to be graphing the points, and then you can get the direction. So you do have to go back to the parametric equations to find the direction of movement. All right, I'm going to pause this. All right, so I'm back. So let's look at our next example. We want to graph the plane curve defined by this parametric equation. X is equal to 2t plus 5. Y is equal to square root of 4 minus t squared. And t uses values from -2 to 2. All right, so let's look at some values of t and resultant values of x and then y. So we're going to vary our t values from -2 to 2. Again, I could have used numbers between those, but as we saw in the parabola above, those were enough to give us an indication that it was a parabola shape. We could have found a whole lot more of the values and we would have gotten more points on that curve, but I think we had enough, so I think we're good there. All right, so substituting -2 into the x equation, you get 1, and then when t is -1, you get 3. When t is 0, you get 5, 7, and 9. Okay, t squared. -2 squared is 4. 4 minus 4 is 0, so the square root of that is 0. T is -1. 4 minus 1 is 3, so that's the square root of 3. 4 minus 0 is 4. Square root of 4 is 2. When t is 1, you get square root of 3. And when t is 2, you'll get 0. So with those values of x and y, looks like x is again going to be positive numbers only, and y is also only positive numbers. So I guess I could have made the x-axis a little bit lower in the field. Oh well, not going to hurt anything. So 1, 2, 3, 4, 5, 6, 7, 8, 9 for x. Y only gets up to 2, so I'm going to make those marks a little bit further apart. All right, so 1, 0 when t is -2. 3 square root of 3. We know that square root of 3 is somewhere between square root of 1 and square root of 4, so somewhere between 1 and 2. So I'm going to guess that it's about right there. You can take your calculator and figure out what it is exactly. I think it's about 1.8 or 1.9 or something like that. But that's close enough. We're not going to be able to see much of more clarity than that with this. So that's just fine. All right. Then 5, 2, 1, 2, 3, 4, 5, 2. Um, 7, 6, 7, square root of 3. And 9, 0. So do you know what this curve is? Well, it could be a parabola, could be part of a circle maybe, part of a hyperbola, part of an ellipse. Kind of hard to tell. So we do know that it's going to be a curve because it's not a linear thing. So I'm going to draw a curve here, not knowing exactly what curve I'm drawing, and indicate the direction of movement. So let's eliminate the parameter for this one. I think the x equation is easier to solve for t. So that's going to be my choice. I'm going to subtract 5 from both sides and divide by 2. So I get x minus 5 over 2 equals t. And then I'm going to substitute that into the other equation for t. So I'll get y equals the square root of 4 minus x minus 5 over 2 is replacing the t, quantity squared. All right. So if you look at this equation, you might notice that before we do anything else, the square root of something is always going to be 0 or bigger. So the implication here is that y is going to be greater than or equal to 0 only. So whatever this equation is, we're only going to graph the parts where y is greater than or equal to 0. And if you look at our graph, of course, that's what we did, and that's what we got. So now, if this is one of our conic sections, we don't have radicals in those. So to get this in standard form, I'm going to square both sides first. And I'm going to go ahead and distribute that squaring in that fraction to both the numerator and to the denominator. 2 squared is 4. And when I look at that, I've got an x squared fraction and a y squared term. So it appears to me that this is not a parabola. So it's either a circle, an ellipse, or a hyperbola. So in order to see which one it is, I'm going to write it in standard form. And since I have fractions, I'm going to write it in the form where it's equal to 1. Fraction plus or minus fraction equals 1 is my goal. So I'm adding the x fraction to both sides. And then, of course, I can't leave it as equals 4. So I have to divide both sides by 4. And that will give me x minus 5 squared over 16 plus y squared over 4 equals 1. And that's the equation of an ellipse. And the center of that ellipse is 5, 0. If you look up at the graph, of course, we do have a center that makes sense. 1, 2, 3, 4, 5, 0. It's right there. So that makes sense. The x radius is 4. That's true. That's the x radius of 4. And we should have a y radius of 2. And that's exactly what we have. Y radius of 2. And notice we only got the top half of the ellipse because the original equation for y only allowed for numbers for y that are 0 or larger. And so that's how we got only that half of the ellipse. All right. So the addendum we would make to this is what we said earlier. It's that equation, but only graph the y values that are 0 or bigger. And to get the orientation, we'd have to refer back to the parametric equations. All right. So let's do this one. Graph the plane curve defined by x equals t squared y equals t squared for t in the set of all real numbers. So we're using everything, all t values. All right, so, oh, and by the way, the process, again, where we got rid of the t is called eliminating the parameter. So that this equation that we have up here for that ellipse doesn't have the t in it, and it's one of our normal standard equations that we know how to graph. That's good for confirmation if you've already graphed it. It's another way to graph as long as you pay attention to restrictions, like on that last one, y had to be greater than or equal to 0. Speaking of that, if you notice x is t squared, that means that x is going to be numbers that are greater than or equal to 0 only. And that means that for y, the same thing is going to be true. All right? Doesn't matter what t you put in, you can't get a negative answer. So since we're going from negative infinity to positive infinity, that's a lot of numbers to try to get. So we're not going to try to get all of the real numbers, but we are going to pick t values that we hope will provide us with enough information to figure out what's going on. So I'm going to start with -3 and do some of the integers. And I'm going to go all the way up to, I guess I can go to 3. Gives me a sense of symmetry if I do that. All right, so squaring t will give us x is 9, and of course y is the same thing. For -2, we'll get 4 and 4, 1 and 1, 0 squared is 0, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So graphing this in the xy plane may not graph all the points that we find, by the way. Sometimes we end up getting really big values that really just help us know where it's headed. If I'd gotten a value that was like 25 or something, then I would have just known to make it go toward where 25 would be. See, I'm only putting 6 marks on the y-axis because that's all the room I gave myself. So I may not actually graph every one, but that's okay. So -3, we're at 9, 9, so we're up here someplace. We'll just pretend like that's where it is right there. Negative time negative, oh, that's time -3. T is equal to -3. When t is -2, we'll be at 4, 4. Time -1 will be at 1, 1. And at time 0 will be at 0, 0. Since x and y are the same value, you may know that that implies that we're going to have that line y equals x. So we can see that taking shape. So I'm going to draw the line, and it's moving this direction until we get to there. So we're moving this way along the curve. Then what's going to happen is we'll start going with positive t values. When t is 1, we'll be at 1, 1. T is 2, we'll be at 4, 4. When t is 3, we'll be at 9, 9. So starting at 0, we're going to be going back, tracing back along that same line. And that's why I did it in a different color. And our direction of movement now is indicated by the greenish arrows. So this was the particle goes from infinity and up where x is really large positive and y is really large positive, comes down along the line y equals x, gets to 0, 0, turns around and goes back and goes out that same direction forever. So that graphs this. Actually, this is a ray that we would consider that. So since x is equal to t squared and so is y, you might see that the elimination of the parameter is just going to be by substitution. So y equals t squared. If I take out the t squared and replace it with x, which is equal to it, gives us the equation y equals x. Now, how are we going to say that we only want the values that are plotted? Is it sufficient, for example, to say that x is greater than or equal to 0? Yes, that is sufficient. Doesn't indicate the direction of movement. I could have also said y is greater than or equal to 0, and that wouldn't have changed the points I graphed. So one statement like x is greater than or equal to 0 is sufficient. So that's all I'm going to have to indicate. Now, one thing that you might encounter is that parametric representations of a curve aren't always unique. So, for example, could I have had, for this same problem, x equals t to the 4th, y equals t to the 4th for all real numbers? Well, for various t values, I'd get different answers, but I'd still get that same set of points that I just graphed. The locations, t equals -1, for example, or t equals, well, that one actually would be in the same place because -1 to the 4th is 1, just like it was for squaring. But if we did t equals -2, that would be 16 and 16. So the location of the point would change to a different time, but it would still produce the exact same graph. So if that's true and you're asked to find the parametric equation for something, the easiest answer is to, like, let's say you want to do y equals, let's say 3x squared plus 5x. And you were asked to write that in parametric form. There are lots of complicated things you could do, but the simplest is to let x be equal to t and let y be itself, but with every x replaced by a t. So y equals 3t squared plus 5t. This set of parametric equations is equivalent to the function y equals 3x squared plus 5x. So that's a pretty easy substitution to make. So with that in mind, we're asked to find two parametric representations for the parabola that's given. Let me write down that equation. Y equals x minus 2 quantity squared plus 1. All right, so the simplest choice for the first one is to let x equal t, and y will be t minus 2 quantity squared plus 1. That's the easy one. That's the one that's going to be the fastest and easiest to get. You could, for example, and this is not a unique answer, I'm just making up something, but I see that t minus 2, so I'm going to do something kind of tricky here, and I'm going to let x be t plus 2. I could make x equal to anything in terms of t, but this one's going to give me kind of a cool result, as it turns out. So y will be t plus 2, oops, forgot to write the plus sign, t plus 2, replacing the x, minus 2 squared plus 1, which simplifies to be x is t plus 2, and y is going to simplify to be t plus 2 minus 2 is t plus 0, so that simplifies to be y equals t squared plus 1. These two sets of parametric equations will both graph the points on the parabola given. The location of the point at time 3, let's say, will be different, but the set of points you get as a result will end up being the exact same set of points. So that's kind of an interesting thing. Oh, and in both cases, we're going to let t be all real numbers, and that's going to create the entire parabola. So these are the values of t. So let me write this correctly. So t is in the range of values from negative infinity to infinity. All right. So all right. So one of the main reasons we talk about parametrics is being able to find out when something is going to be at a particular location, so that parameter of time becomes important. Physical location x and y at a certain time for like a projectile, if you want a rocket that's launched to well, I guess it would be a bomb because it would be taking the parabolic path. So anyway, that's not a very nice example. But anyway, if you want to know when it's going to strike, when you launch it at a particular time, then parametric equations would be good. So many times when we have projectile motion, we'll be using parametric equations. And t will represent time, as I've been saying over and over. All right, so let's say that the motion of a projectile moving in a direction at an angle of theta equals 45 degrees. With the horizontal, and we are, to make this easier to deal with, going to neglect air resistance as a factor. The parametric equations for that will be x equals the initial velocity times the square root of 2 over 2 t, and y will be v sub naught, initial velocity, times the square root of 2 over 2t minus 16t squared. For t in the range from 0 to some unknown number k. Where t is measured in seconds, v sub naught is the initial speed of the projectile in feet per second. x and y are in feet, and k is some positive real number. We're going to first find the regular form of the equation, and then we're going to graph both forms for an initial velocity of 128 feet per second. All right, so those are the directions. So the best one to solve for, I think, is going to be the x equation. So I'm going to solve it for t. So to solve for t, I'm going to divide both sides by v sub naught times square root of 2 over 2 to get t by itself. And then I'm going to take the other equation, the y equation, and replace the t in each case, because it shows up twice. I'm going to replace that t with x divided by v sub naught square root of 2 over 2. You might have noticed I didn't simplify that complex fraction. Oops. Because I was looking ahead and I saw that the square root of 2 over 2 was going to cancel nicely, so I didn't mess with it. All right, anyway. So this would be 16 times t, which is x, over v sub naught, times the square root of 2 over 2, quantity squared. So in the first term, the v sub naught and the square root of 2 over 2 cancel each other out, leaving x. And then distributing that squaring, that 16 is going to be multiplied by x squared over the denominator squared. And I'm going to distribute the squaring in the denominator as well. So that'll be v sub naught squared times square root of 2 over 2 squared, which will be 2 over 4. And so that simplifies to be 16x squared over v sub naught squared. And of course, 2/4 reduces to 1/2, and to divide by 1/2 is the same thing as to multiply by its reciprocal. And so we end up getting y equals x minus 32 x squared over v sub naught squared. And if you look at that equation, you might notice that that's a parabola because only x is squared, not y. And the number in front of x squared is negative, which means it's either going to open left or down. And because x is squared, that means it'll either open up or down. So putting those two ideas together, it's going to be a parabola that opens downward, which is kind of what you'd expect for a projectile motion, is that if it starts, say, right here and moves along the path of a parabola, we're going to want it to look like that. Think about a football being thrown or a golf ball being hit. It's going to follow a path that looks sort of like that. And the initial velocity was 45 degrees. So at the outset, the velocity is a 45-degree angle. So that theta is 45 degrees. And if I were to draw in this, the x part of that is going to be v sub naught times the square root of 2 over 2t. And the y part of that is going to be v sub naught square root of 2 over 2 t minus 16t squared. So there we go. There you have it. So that ends this lesson. I will see you later. Have a good one.